Right, so how do we prove this? How do we prove that? How do we prove this theorem in general? Okay, so we looked at two special cases where k is equal to 2 and k is equal to 3. But it turns out you can use you can generalize this type of argument. So how do we prove that the edge connectivity is at least k minus 1, where k is a chromatic number and G is K critical. Right, so what you do is you take the graph G and basically what we do is we delete, we let S be an edge cut, right? An edge cut equals to lambda of G. Now, what is this edge cut? If I remove these edges, that's my, what we're going to do is we're going to delete those edges, and we're going to have two graphs that result, G1 and G2. Now, G1 can be colored with at most K minus 1 colors, or we can color G1 with K minus 1 colors, and we can color G2 also with K minus 1 colors. Right, so this is G1, okay, and that section there is my graph, that's G2. Okay, and again, like I said, you can use K minus 1 colors to color G1 and G2 respectively. You can use the same colors. So now let U1, U2, U3 up until UK minus 1, let that denote the color classes, and W1 up until WK minus 1 denote the color classes. Now, if we look at the set UA, where A is a color, right, and the color A goes from 1 up until K minus 1, then what we do is we define the set SI as the set of all edges that go between UA and W subscript I plus subscript A plus I. Okay. So if you look at U1 as an example, then we look at let's look at S. Now, if we look at color 1, right? If we look at U1, and we look at W1 plus 2, right? Now, how many edges are there between color class U1 and W3? There is this edge here. We count that edge there, right? And let's call this this index I, let's call that index 2, right? So again, the number of edges between U1 and W1 plus I is, in this case, 1. If you look at the second color, U2, the color used in U2, how many edges are there between U2 and W4? Okay, so here's U2, and edges, well, we haven't indicated that yet, but we go and count those number of edges. And you go up until you get to uj minus 1, and you look at all the edges between uj minus 1 and color class wj minus 1 plus I, and you carry this process through until you get right to the last color UK minus N. With each time you count those number of edges. You throw all those, and again the indices you mod by K minus 1. And you throw all those edges in a set S, and you call this set S subscript I. So S subscript I corresponds to all those, the edges that you counted. Right, so if you look at as the special case where k minus 1 is equal to 4, then if we look at S1, S1 is going to be, so you look at, you count all the edges between UA and WA plus I, and then you remember you're taking, you're modding that by k minus 1. So for U1, you go and count all the edges between U1 and W2. In this case, that's empty there. Then you go to U2 and you count all the edges between U2 and W3. Remember the index I is 1. So then you count all those edges, that's empty. Then U3, again, you count all those edges there. And then U4, you're counting the number of edges between U4 and W4 plus 1 mod 4. So you're counting all the edges between U4 and W1, and that's how you work it out. So in that case, it is clear that S1 is empty in that case because we've not counted any edges. Now for S2 equals 3, for S2, now your index I is equal to 2, so that is what it's going to look like there. You're looking at the number of color edges between U1 and W1 plus 2, which is W3. You're counting no edges there. Then you're looking at the number of edges between U2 and W2 plus 2. There you've counted one edge. Then you look at the number of edges between U3 and W3 plus 2 mod 4. 5 mod 4 is you're looking essentially at the number of edges between U3 and W1. There you've counted another edge. And then lastly, you're counting the number of edges between U4 and U4 plus 2. 4 plus 2 mod 4 is 2. So essentially you're counting the number of edges between U4 and W2. And there you've counted another edge. So in total, you've pretty much counted 2 edges. Okay? So that's how these sets, the S sets, are defined. Now what they claim is that for some index I, where I runs from 0 to k minus 2, for some I, we have that some Si is not empty. Okay, what happens if it is the case? What happens if some Si is in fact empty? So for argument's sake, let's assume S1 is empty. The proof is the same for all indices I. So let's say S1 is empty, right? So there are no edges between U1 and W2. There are no edges between U2 and W3. There are no such edges. No edges between U3 and W4. There are no edges between, up until the end, between UK minus 1 and W1. Right, now because there are no edges there between those two partite sets, it means that I can pretty much do the following. I can basically take the colors the color that I use in W2, and I can replace it with the color I used for U1. right, like that. Now, if I look at U2, because there are no edges between U2 and W3, I can go and replace the colors of W3 with the color that I used for U2. Like that. Because there are no edges between U3 and W4, I can go and replace the color I used in W4 with the color I used in U3. Let's say, for argument's sake, there I've done the replacement for that particular set there. Okay, and let's call that W4. Right, so I can carry this process through right up until the end. If I go up until uj minus 1, now uj minus 1 I can go, because there are no edges between uj minus 1 and wj, I can color wj with the same color that I used for uj minus 1. Like so, and then if I go to uj, there's no edges between uj and wj plus 1, so I can color the color that I used in uj. I can color the vertices of wj plus 1 with that color. Right, like so. And then once I get to the end, uk minus 1, because there are no edges between uk minus 1 and w1, means I can color the colors of w1 with the color I used in uk minus 1. Like so, alright? And also, again, I would have changed this color as well, because I would have looked at the color I used in UK minus 2, which would have lied there, and that color I would have used there would have been that color there, and so I've pretty much sort of just permuted the colors here, and I will not have any problems here with edges because these sets are all independent sets, right? So I'm not going to have any issues there. And I've basically constructed a coloring that where I'm only using K-1 colors, and we said the graph is K-chromatic, so this is impossible. So therefore we cannot have a situation where one of these S's that I defined is empty. Every one of these S's must have at least one edge. Now it is obvious that all these SI's are disjoint because of the way that they are chosen, these indices, right? So because these SI's they only count possibly partially the cardinality of S, it means that S is at least the sum of these respective cardinalities. Right, so therefore, because each one of them has got at least one edge in, you're going to count at least K-1 edges. So therefore, the edge connectivity of G is at least K-1. Right, so this corollary states that if G is color critical, then the minimum degree of G is at least a chromatic number of G-1. That follows from the previous result, because the edge connectivity of G we know is at most the chromatic number of G-1. Okay, and remember, the edge connectivity of G is obviously at most the minimum degree. Okay, because I can delete the edges incident with a minimum degree vertex, and that's going to give me a disconnected graph. So because lambda is the minimum number of edges I must remove for disconnectivity, it's therefore at most the minimum degree of G. So you can basically then just replace that with an inequality, and you can deduce that delta of G is at least that. Okay, now if G is color critical and S is a subset of G, and S is a vertex cut of G, then the subgraph induced by S cannot be complete. Right, so there's G, and there's the cut set S, which is the subgraph induced by S is a complete graph, and we've got the components H1 up until Hj. Right, so let's define G subscript I as the subgraph induced by vertices of S union with the vertices of the ith component. So G, for example, G2 will be this graph here, okay? It will be that graph there. G1 will be that graph there, okay? And Gj will be that graph there, okay? Now, we know that G is critical. It's K critical. So therefore, the chromatic number of G1 is going to be at most K minus 1. The chromatic number of G2, because it's smaller than G, it's going to be at most K minus 1. And the chromatic number of Hj or Gj is going to also be less than or equal to K minus 1. So in general, the chromatic number of Gi is going to be at most K minus 1 because of the criticality. Okay, so I can basically do a coloring of S. I can first go and color G1 with K minus 1, at most K minus 1 colors. There's G1, and let's color it with K minus 1 colors. Right, so there's my coloring that I'm doing. I am forced for that complete section to color it with all of the vertices with different colors. So that's what I'm going to be forced to do. Right, and I'm coloring that vertex there. G1 colored with K minus 1, at most K minus 1 colors. Let's consider G2, again use at most K minus 1 colors. Okay, and we just make sure that we color that section the same. So there we've got a coloring for G2. We do it in general up until we get to the last one, which is Gj. Alright, so there we've got my coloring, and now putting all of that information together, we get the following. So putting all those components together, back together again, you get the following. So what you're doing with G1 is you're doing that, putting it like that together, superimposing it, and again you're doing that for all the components, and you superimpose that. Okay, and what's the problem with that? This is going to imply that the chromatic number of G is at most K minus 1, okay, because you've pretty much, you've not changed anything there. Those colors, you don't have edges there, so, and you've just superimposed those vertices there. So you've generated a coloring that's got at most K minus 1 colors. So that's a contradiction. So that little section cut set there cannot be